Okay, so Lucas had an excellent question about the homework. How do we schedule the trips, basically? So we have a bunch of passenger requests coming in, and now how do we decide like which passenger should get served next, and perhaps by which elevator? So yes, one possible solution is to implement a queue, right? And you have perhaps a mutex around the queue, because otherwise you'll probably be in trouble. You don't want two threads modifying the queue at the same time. And then you'll just check out the passenger at a time. That's unnecessarily complicated, though. We can do much better than that. Or no, we probably can't perform better than that, but we can do something much easier than that. If you have only one elevator, then you can simply have a lock. You have the queuing kind of comes for free. So you have all these passengers, and they all try to grab the lock. This is basically, imagine that for the entire elevator system, you have to have a single lock to push the button. Right? Everyone else is just sitting there. So, so one passenger gets to push the button, and then the elevator comes and gets them. Right? That's one way to do it. So now, they're already pushing the button. You can't control that. But when you get the request from them, you can just pause that by trying to grab this lock. You can just pause it so that no one gets to get an elevator except this one guy. Right? And when they get served, then the next one comes in. So it's sort of a queue for free. That works with one elevator. Doesn't work with more than one, right? Because now you have a single lock. So now when one elevator is working, that lock is probably being held. So the other elevators can't work. So probably you want to have multiple such locks, right? One per elevator. And then the final question is, well, which lock should a passenger try to lock then? If there's like 4 elevators, which one does it lock? So I think in my solution, I'm thinking of trying to make a better solution, but my solution has just initially, when passengers start out, they just get randomly assigned an elevator. So if I'm passenger 5, I go with elevator 3. And so then sometimes it's not optimal. Toward the end, there will be an elevator that's not used, and it's not going to get a request. But on average, you're going to do well enough. So that's one way to do it. But you can certainly do better than that. So one way would be to have these queues. I think there must be other ways too. I haven't thought too much about it. Okay, other questions on the homework? Yes.
It's kind of a shame that we can't access the actual passenger struct.
You can make your own, huh?
Yeah, but in the air has to have to duplicate work.
Well, if you want, go ahead and copy paste it. The reason, of course, is that we don't want main.c is keeping track of the actual state of the system for scorekeeping purposes, right? To see if you change that, maybe you just say, oh, all the passengers made it to where they wanted to go, and we're done. Of course, you wouldn't do that, but that file can't be changed, and we'll grade it with our own copy of that file. But you'll have most of the information just from those requests, so you can keep track of it. Yeah, try to keep it simple though. I think my solution, and it has a lot of comments and weird spacing and stuff in it, I noticed, is about 3 lines longer than the template. Something like that. Or maybe with the weird spacing it was like 10 lines longer, but there really isn't anything to it. What takes time here is figuring out, like, okay, so barrier, where, like, I should wait here, and I try that, and it never finishes, and then next time it crashes. So that was one trick, with this lock to control each elevator. So I think the passenger is going to have to hold that lock while they're inside too. So it's basically, this is my elevator, that's a lock. That's a handy way to do it. The other one is, right now, the elevators open and close the doors, and we're just basically hoping that the passengers get scheduled first so they can get in before the elevator closes the door again. So what we need to do is have the elevator wait for the passenger to get inside. Right, so I think there's 2 steps here. we also have to have the passenger wait for the elevator to open the door, because you get error message if you walk into the door. So for that, barriers are very handy. If you have a barrier of size 2, remember the barriers are sort of walls that you can push over if you're enough people, right? So we have a barrier of size 2. Now the elevator, you can have the elevator wait. Let's see, how does it go? Start with the passenger. Passenger waits for the barrier to wait for the door to open, basically. When the elevator knows that it's opened the door, now it also waits for the barrier, so now the barrier is open, passenger can go through. Passenger goes inside, and now waits for the barrier again, or actually maybe it's the elevator that starts waiting for the barrier, saying, okay, I've opened the door, now I'm waiting for this barrier again until the passenger comes inside so I can close the door. Right, so you have two of these synchronization places where they have to do it at the same time. So I think I use 2 barrier calls. One to wait for the door to get open, one to wait for the passenger to be inside. Yeah. Other questions? Oh, pretty light in the classroom today. 9 people. What is this? Yeah.
I was running just the template on my Mac, and it ran fine. When I tried to add barriers, it was like not recognizing. It was like saying I was missing operators.
Missing operators?
Yeah, if I tried just to declare a barrier variable, it'd say I was missing operators. But then if I ran the same thing on EC2, it would
Oh, so I think on the Mac the barriers are not in the pthreads library. There's something like that. Yeah. In fact, that's why I've been running it here. I didn't figure it out in time before class, so I was running it on Linux. Yeah, don't have a solution now. If you find one, post it on Piazza. And I'll try to get my shit in order here and get your EC2 multi-core machines up and running too. That's not going to be the same machine. EC2 doesn't let you change the machine type on the fly. So you're going to get a whole other set of machines. You're going to have to just hunt for it, find the right one in the list and start that one. Yeah, you'll have the same key, I think. I don't really remember how I set that up. Professor Kanish helped me out. So. No, Kanish. Keep saying it wrong. Now it's on record. Okay, so the topic of today then was, what was it? Ah, yes, deadlock. So you will find out, probably, when you're doing this homework, that every now and then the program just stops. So let's try to figure out why that might happen. What is this? Ah, notes. Good. So let's start with a very simple example. We have two threads. They both, no, let's see. Yeah. First thread goes like lock A, and it says lock B, because it wants to operate on maybe a couple of different data structures, and they're both protected by different locks. So there's data structure something that's protected by A, and some other data structure is protected by lock B. So we need both locks in order to make our changes. So we lock both of them. That's fine. And then we do some critical section work here, and then we unlock. Let's move this up a little bit. Unlock A, and we unlock B. Okay, so then comes our second thread. It's running this function G. It says lock B, lock A. Do some more critical work here. Unlock B, unlock A. And that's it. Okay, so we run this in 2 different threads. One thread runs F. Whoa. One thread runs F, one thread runs G. And it so happens, well, it turns out that this doesn't go anywhere.
F starts, gets the lock on A, and then G gets the lock on B, and then we start. There's a then.
Yeah, so there's no guarantees on the execution order here. So sometimes you'll have F going lock A, B, right? And it runs fine, and then G comes and locks B and A and runs fine. It's no problem. Sometimes you'll have the other order, but then sometimes you get a little unlucky, so now you have F locks A, G locks B, and now F wants B and G wants A, and they're kind of locked in this deadly embrace, and they can't get anywhere. So that's a deadlock. It happens all the time. If you write your program a little sloppily, it happens all the time. It won't happen if you have a single lock. If your program has a single lock, it just can't happen. So that's nice. But if you have a single lock, usually that means your program's not going to run very fast, because now it becomes sort of a serial program. There are all these critical sections. They're all these different threads. They all want to get that lock. So now they can only run that at a time, one at a time, and now you only use one core at a time. It's kind of wasteful. So in this particular scenario, can you think of a way to solve it?
Lock A above lock B and G.
Let's see. Here, and we'll move this up there. Okay. Let's worry about this one first, and then we'll see if maybe a barrier might be a different solution. What do you think? Is this going to solve the problem here?
Yeah.
Yeah, takes care of it. So now we got the right order here. So if you lock A, there's no way G is going to come in and lock B first. So there's no problem getting B, and then we're all set. So that seems pretty easy. Unfortunately, it's not always that easy, because oftentimes this locking B here doesn't happen in there. It goes something like, oh, subroutine B, right? You call that, and that makes the locking happen inside of there. So it's very difficult to get this right, because you don't necessarily control the locking order, right, in one function. So in general, actually let's move on to a more conceptual picture here. I had something nice. So deadlock is, so there's two main problems in concurrent programming. It's deadlock and it's race conditions. Race conditions is this thing where you're trying to access some data and it's unprotected by a lock. And every now and then you get unlucky and the result turns out non-deterministic, right? Deadlock, now you put a lock on it. Unfortunately, you did it wrong, and now the program won't run at all.
Can the program still be undeterministic even if you have a lock? Because from time to time, like some other thread will hit the lock first.
Yes. So the result is still non-deterministic, but at least it's always correct. So you're not going to get some weird result in there, but you don't know which one out of two possible correct solutions will come out. That's always the case in concurrent programs, except for the stuff that Tim's working on, deterministic concurrent programs. So I don't know if you've heard of this one. It's the dining philosopher's problem. So we have these 5 philosophers, and there's supposed to be a rice bowl in the middle. I don't know where it went. Okay, so they're sitting around the table. There's a rice bowl, and they want to eat, right? And there are these 5 sticks. So they're eating with what do you call these eating sticks?
Chopsticks.
Chopsticks, yeah. Well, you don't chop with them either, do you? Yeah. Okay. So here's the problem. Now all these philosophers, they're running the same program. Right? So philosophers, they like to be strict, right? About their thinking and their actions. So now they're all doing the same thing. What we do is we first pick up the stick on the right, and then we pick up the stick on the left, and then we eat until we're satisfied, and then we put down the sticks. That's a good eating program, right? So in this case, every philosopher picks up the stick on the right. He picks up this one, 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 she picks up that one, and then now you're just going to pick up the stick on the left, but of course they're all already picked up. So they die. So this is starvation. Right? It's a deadlock actually, but starvation can be quite similar. So, so in this case, now we have everyone's got one stick, everyone wants the other stick, but they're kind of stubborn. They're not going to put down the stick. And that's the general deadlock situation. Okay, so what can we see about this that characterizes a deadlock? Okay, characteristics of deadlock. So this is a little bit on the theoretical side, but it's very good to know if there's some easy solutions. So the first thing here is only one philosopher can use each stick at a given time. Right? So that's called mutual exclusion. Okay, the next piece here is we have two. Well, I guess that's not really in here, but there has to be two resources. If you have a single one, there can't be a deadlock. So there has to be at least two resources in the system. Why don't we write that in here too? Okay, so next is once you get one of the sticks, you don't put it down until you've finished eating. All right, so in this case, you don't get to eat, but you still don't put down the stick. And that's called hold and wait. All right, so if you try to grab a second lock, you will hold on to whatever you had before. Okay, and then you actually never stop holding it. So no matter how hungry you get, you're not going to let go of the stick. Because then someone else gets to eat. There may not be anything left in the bowl in the end. So this is a problem. We make sure we hold the stick. So that's called no preemption. Actually, just spell like that. So you never interrupt your holding of a lock until you call unlock from a proper execution point of view. And then finally, there's this circular dependency. So in this case, it's pretty obvious we have a circle. Right? But even if you have two, like we did in our case up there, if we have just two locks, you have one thread holding one lock, one thread holding the other lock, and they each want the other ones, that's a circular dependency as well. If you have a circular dependency, well, now the deadlock is complete. If there is no circular dependency, if this was a line, let's think of that. What would happen then? So let's see. So you put another stick over here, and then we split it out. It's too tricky. Let's maybe I can draw it. Okay, philosophers. 1, 2, 3. Not exactly on the line, are they? They're not even the same size. Well, philosophers don't have to be the same weight. I can align this. Where is it? Okay, so then we have some sticks. Same situation, right? What did I do? Did I hide it? Come on. Oh, my dock won't show up. Okay, where is it? I must have closed the... Yeah, I did. Okay, sorry about that. So we have some sticks. More sticks. One more. Okay, so now we have, there's no circle, right? There's no circular dependency, but we still have the same problem, I suppose. So now we start with the right stick. I get that one, I get that one, that one, that one, and that one. They all hold their right stick, and then what? He actually gets to eat, right? So then he's done. He puts down his sticks, and he gets to eat. Puts down the sticks, and so on, and there's no problem. But if this was the same stick as that, then it doesn't work anymore. Okay, so if you want to have a deadlock, actually we can remove this one here, because you can't have a circular dependency if there isn't at least two resources. Where would the circle be? So these are not just characteristics, these are necessary conditions of deadlock. So that's pretty neat. Because now if we make one of these go away, then we are guaranteed there won't be any deadlock. Alright, so we can try a few different things. We can try to remove mutual exclusion. Maybe that doesn't work so well for the philosophers, right? Because then we have to break the sticks. And yeah, if they're just having a tug of war, that's not going to work. Okay, so we have to have mutual exclusion. The hold and wait is not necessary. Alright, so why don't we try that? So instead of picking up one stick and then taking the other stick, I'll say I pick up one stick, and then if the other stick isn't available, I put down my first stick. What do you think? So this is a pretty different, if you think of it as in a program point of view, the mutex lock function, it wouldn't hold then. It would just return, probably. Or alternatively, it will release all the locks for you. That's another option, right? So I'm holding one lock, I try to lock another lock. This mutex lock function just releases the other lock for me for a while until I'm ready to continue with both locks. But let's try it in the philosopher case here. Let's go back to the round table here. Okay.
It would work unless they all pick up the sticks at the same time, set it on the same time, all pick up at the same time.
Yeah. So now all these, it's actually a very good point. So all these philosophers, they start out taking up the right stick, right? And they see the other stick, oh, it's gone, put it down. And we do it again, right?
It's unrealistic that it will happen every time.
It may be unrealistic, but it can happen. And unfortunately, when you have, at least if you have a computer that's pretty reliable in terms of timing, once it happens, it's not going to go away. So what you might need is to make sure you have some randomness in the system then. So instead of picking up the stick and then putting it down right away, maybe you wait for a little bit to see if the stick becomes available. You wait for a random amount of time, and then this is going to be safe. Okay, so that's one option.
Only pick up sticks when you're in an odd number, and then wait. If you're an even number, just wait until they become available.
Ah, let's see. So we go 1, 2, 3, 4, 5.
1 and 5 on
These two are together, but that's maybe okay. So you only pick up the stick on the right if you're the odd number?
Yeah.
I see. So we do some sort of turn-based thing here. So everyone agrees that now is turn 1, and then you go, okay. Yeah, sure, so that'll work. Now we have to have some agreement on which turn it is. Someone has to decide, I'm the one to update the turn, and so on.
But number 5 wouldn't be able to eat, because 1 and 5 would pick up the right sticks, and then 5 would be stuck.
That's true. So maybe not odd numbers, maybe you go some other, yeah, some sort of arithmetic will work out, I think. Okay, so that seems like one option here. It does get relatively complicated. So if you let the system, if you automatically drop a stick whenever whatever other lock you want is unavailable, then you might end up in a situation where you actually never get to go. Like now you try to pick up the other one, and now the first one becomes unavailable. Right? And it's a bit of a challenge. So it might be better for the mutex lock function to just return saying, no, couldn't do it. Right? So you get sort of an error code back, and then it's up to the programmer to release the other lock. Right? So this becomes a difficult program to write. It's hard enough the way it is. Now if you start not being able to get the locks, certainly much harder. And it may be sometimes you forget to release the stick, right? You just put the stick away in your pocket and you continue, and then now there are no sticks left on the table. Okay, so, and that's a buggy program, of course, but buggy programs are very, very common. Okay, so that's one option. Let's think about other options. So no preemption. So in this case, preemption is not, oh, I couldn't get it, so therefore I put down the other one. The preemption is, I'm holding on to this, someone else comes in and takes it, basically. So in some computer systems, the OS will monitor, the OS or the runtime system will monitor all the locks and see, okay, this lock has been held for way too long, or it's been holding and waiting for way too long here. I'm just going to stop it so someone else can get it. Deadlock prevention systems do that. So you can have a separate little program that just keeps track of things and eventually decides who should not get to eat right now. But again, that gets very tricky because now you have your program and there's going to be some error handling there. It's got probably your whole program, your whole philosopher may have to go. Right? There was deadlock here. We don't, some sort of undefined weird state. It might be easier to just kill the philosopher, put in a new philosopher. If you care about your programs or philosophers, then that may not be the right way to go. And then finally, there's the circular dependency. So that one turns out to be the easiest.
Give everyone 2 sticks.
Yeah, that would work too, yeah. Yeah, then there's no dependency. I mean, you don't always have that luxury, right? There's oftentimes there are shared data structures, and making copies of it's not going to work. But actually, the solution that you proposed for the original problem here is exactly this. Now we're removing the circular dependency. So it used to be G goes B to A, F goes A to B, and now you got this circle. But if we can tell them a different order, so we say locks have to be acquired in a certain order. They have to go alphabetically here. There cannot be a dependency if you always acquire locks in a predefined order. Right? Just like here, we go first A and then B, and we're good. Let's see if we can do that over here. So we already did that. We said first the right and then the left. It didn't work. What's wrong with that? We had a predefined order. So then we're not supposed to have a circular dependency anymore.
Because that one, they're both dealing with the same right. Like A and A are the same, so it'd be the same right stack.
Exactly. So there was a predefined local order here. We tell the philosopher, you're right, you're left. But that's not the same as someone else's right and left. It has to be a predefined global order. So let's try that instead. So now we put in a global order first. We say 1, 2, 3, 4, and 5. Okay, and now the rule is, you don't pick up the left stick or the right stick. You pick up the lower numbered stick first, and then the higher numbered stick. Okay, so this guy gets to go first. He picks up this one. He goes, can't do it. Right, that's the lower number stick, so he's just waiting for that stick. Next one is able to pick up this stick. Next one, no, let's see. Lower stick, yeah. This one is able to pick up that stick. And this one picks up that stick. So number 5 never got picked up, which means this philosopher gets to pick up number 5, and now they can eat. Now he can eat. Did anyone else get to eat? No one else got to eat. But then this philosopher is done, puts down both sticks, so now this one gets to eat, and that one gets to eat, and so on. Is there a question? No. All right, so in general, so what you want to look out for, I think, when you write a concurrent program, unless you have some fancy deadlock prevention system, which does exist, which you probably don't want to write yourself, but there are in some languages, say in SQL for databases, they have deadlock prevention systems, at least if they are transaction databases. Unless you have one of those, what you always want to do is make sure that you lock in a globally defined, predefined global order. And then you're going to be good. So that's pretty much all there is to deadlock. It's not so easy though, right? Because you'll have some functions that you call, they want to lock A. Right? You already locked B. You're modifying this data structure. This data structure that's shared, you need to lock B. And now you call this function to help you out with something. Say it's printf. Printf needs to lock some buffer. They lock A. And then you have some other program that needs to lock A first. Some other part of your program that needs to lock A first, and then they call some function that locks B because they need B. And now you have now you're locking it in the wrong order again. You have a circular dependency.
If you get somewhat of a large program, it becomes a disaster in most things, unless you can somehow create a structure to show what's going to happen.
Exactly. It becomes something of a disaster. Yes. So now we need to think about ways to deal with this. How do we make this a little easier to handle? And the most common way to do it is called a monitor. And I'm sure you have dealt with monitors before. You may not know it. So what's a monitor? It's a data structure with built-in synchronization. Okay, so what does that mean? A data structure, right? It's just data. How can you put synchronization in a data structure? Can't do it. And if you just have a struct, a C struct, there's no way to enforce synchronization on there, because they're just pieces of memory. So the way it goes is you have hidden data, and then you have accessor functions. Right, so the data you're not supposed to access. Well, you can. In C, you can always access the data directly, but if you do, expect mayhem. Right? Otherwise, use your getters and setter functions, and they take care of the synchronization for you. So now you might have, say, a hash table. Right? You're not playing with hidden data. You need to have locks on this hash table, but the locks are built into here, right? Built into the monitor. So now when you call get, you're guaranteed that you're not going to have any race conditions, and then hopefully, well, if you write the monitor correctly, your monitor inside, it's not going to be trying to access locks outside of this data structure. Right? So you're not going to get a circular dependency there. It sort of becomes the terminal of a tree. Okay, so it's usually pretty easy to write a monitor because it's a very small piece, right? It's just your little hash table. And then you know that, okay, those pieces are thread safe, so then whatever you write outside is making things a little easier, a little better for you. Let's see. What am I saying? Whatever you write outside becomes much simpler because all the integrate details of the data structure are hidden, including the synchronization. So some examples of monitors that we all use, an operating system. That's an enormous monitor, right? The operating system is full of locks all over the place, but we never see them. We just make these function calls or system calls, and the locking kind of happens inside. The operating system never depends on any locks outside in my program. So there can't be a circular dependency there. I'm going down, but they're not depending back on me, so we're okay. I think the buffered I/O, so printf, I'm pretty sure it's thread safe. Excuse me. So when you call printf, it's going to be grabbing a lock. Of course, printf isn't grabbing some other lock than that is in your program. Right? It's self-contained. So now printf grabs some lock. You don't know about it, but it makes sure that you don't have lines that sort of interleave. You have first one line and then another line, even if you have threads that print at the same time. This is assuming that printf actually does that. I'm not sure. But in general, anything where it says, oh, this data structure is thread safe, it usually means that this data structure is implemented as a monitor. It has some built-in synchronization operations. I think later on in the, well, toward the middle or latter end of November, we'll try to make some data structures that are thread safe even though they don't have locks. That's a whole other game there. Let's see. I need to plug in. Okay, so those are deadlocks. Let's switch tracks a little bit then, and actually, any more questions on deadlocks? You're going to run into them. All right? Even for this homework, you're most likely going to have deadlocks. So for that, try to look for the circular dependencies first. One easy way to avoid it, to avoid your deadlock, usually, I don't know, in this case. Usually you can switch to having a single global lock and your program is going to work. It's just going to be slow. In this case, if you start using a global lock to do, using your lock to do other things. So in this case we were saying, oh, use it to hold the elevator, right? The passenger gets to keep the elevator. I don't know, the elevators are going to need locks too, I think. If they use the same lock, probably everything's going to get screwed up anyway. I'm not sure. So there are other ways to get deadlocks than just by regular locks. You can write programs that depend on each other in a circular way, and they will also deadlock. I can't think of a good example right now. Okay, so let's talk about the last piece then. We discussed condition variables too before, where you can wait for a condition variable and then you can signal the condition variable, and whoever is waiting for it wakes up. It turns out there's a basic primitive that can do both. It's called a semaphore. Semaphore was, I think, the first synchronization primitive that was described properly. Let's see, call it semaphore. I think it was Mr. Dijkstra that came up with it. Edsker? Is that his name? Yeah. Anyway, so a semaphore has two operations. Semaphore is just like a barrier. It has a number. If it's a binary semaphore, you start with a number 1, but you can have any number in there as long as it's positive. So it starts with positive number, non-negative number, sorry. And the constraint, the semaphore constraint, is the number may never go negative. So that's an invariant on a semaphore. We know that can never happen. Okay, and now we have two functions. There's one called wait, or it's actually in the original, since Dijkstra was Dutch, it was actually called P for proberen, or trying. But so you'll see P sometimes, you'll see it in a textbook as well. And that actually, if it works like this, if the number, or if I'll just call it, if the semaphore is greater than 0, reduce by 1 and continue. As wait. For the semaphore to above 0. Okay. What do you think the other one's going to be called? Notify would have been nice, wouldn't it? Unfortunately, it's called post. And just to make things worse, because that one's called P up here, and now this is post. Yeah. And then there's the V. That's the other name in Dutch. Verhogen, for raising the value. Raise the value. Raise the semaphore. So every time you call post, the semaphore value goes up by 1. Every time you call wait, it goes down, unless the value is already 0, in which case you have to just stop and wait for it to go up. Okay, so this primitive actually lets us implement both mutexes and conditional variables. Let's see, I don't know about barriers. Yeah, barriers too. Yeah.
Semaphores. I've vaguely heard about semaphores. Does it also have something along the lines of terrain instead of symbol?
Never heard of that. There might be, so that's not at least the standard primitive. There might be some extra features in certain implementations. So let's see. How can we implement a mutex using a semaphore? So this is somewhat relevant because Linux, or I don't know about Linux, they may have both, but it's not uncommon for an OS to only provide semaphores, and then you build other things on top of it. And it's nice because it's so hard to write these things, it's very hard to implement a mutex correctly, or implement a semaphore or a barrier or something. It's nice if there's only one piece you have to implement, and then you can build on top of that to make all the higher level primitives like mutex, barrier, and condition variables. So let's try to make a mutex. A mutex is a binary semaphore because there's only one thread is allowed in. So we start with a semaphore equals 1. So now if you want to grab the lock, what do we do? The lock implementation becomes just wait. Right? That decrements it and continues. If it already is 0, then we have to wait. Okay, that's good. What about unlock? Very straightforward. Post. Okay, and we're done. There's our mutex. Okay, let's try a barrier.
Call wait. Should I equal to this?
Wait the amount of times that there is, right?
Call post. However many people you have wait.
I lied. We can't do a barrier very easily. We obviously can implement a barrier using, but we need a little more. So we'll have to wait with that until next time. But let's do a condition variable instead. So now we have a condition variable, meaning we want to be able to wait for something until someone else tells us we're ready. So let's try a condition variable. What value should our semaphore have? 0, right. Because right now, if we just call wait, we should be waiting. Nothing should happen, really. So now, our wait for the semaphore becomes... What does it become? Just wait, yeah, exactly. Because it's 0, so wait. If we call wait, We're going to wait until something happens. And then, what's the notify? It's post. So that's pretty nice. Turns out condition variables and mutexes are the same thing, only upside down. But if you look at it, you couldn't actually implement. Yeah, this actually works the other way too here, right? You can post before. It's even a little better than the ones we usually see. You can notify first, and then you call wait later on, and it's going to go straight through because it already was notified. That's interesting.
You can wait twice in the mutex, right?
By the way, with a barrier, don't you know?
Yes, so you can, if you have multiple different ones waiting, then only one of them is going to get woken up. Call post, only one of them wakes up.
Turn a mutex into a condition variable, you can just wait twice. Semaphore equals 1 and still wait twice. Decrement it, and then it would actually wait. Right?
Wait twice. But how do you can't get through it. You want to turn a condition, which one do you want to?
I was talking about the mutex.
Mutex into a condition variable.
Yeah. So it's equal to 1, so you wait the first time, it reduces it by 1, then you wait again, and you're at the same position you were when you started the condition variable, right? I don't see why you'd ever want to do that. But
Yeah, it'll make your. I mean, it kind of is very weird from a mutex abstraction, right? You want to lock it and then unlock it, but of course, if you look at the implementation, it's obvious they're the same stuff, so you can use it any way you want.
Do these operations have to be atomic?
These, well, not the whole thing. We don't actually care how the implementation works in the OS. From a correctness point of view, it'll always work if this is correctly implemented. But yeah, we're out of time. But next time, we'll look at how an OS might implement this. And one very nice thing about semaphores in OS implementations is that they're not spinning. So you call wait, and that just puts your whole program to sleep until the semaphore becomes available. So we'll see how we implement that next time. So unless it's perfectly obvious, we're talking about concurrent programming here. You want to be reading the concurrent programming chapter in the textbook. And there will be concurrent programming things on the midterm as well, which is next week. When is it? Is it Wednesday or Friday next week?
Friday.
Okay. Everyone seems to be in agreement about that.
Everyone what?
Seems to be in agreement that it's on a later day. Yeah.
So don't check.